All right, so rotations is the next transformation that we're going to talk about. So rotating an object certain numbers of degrees around the origin there is what we're about to do. So a turn around a fixed point called the center of rotation. So we're going to do counterclockwise around the origin is where we're going to center all of our different rotations. So figure rotates a specific angle and direction. And we're going to talk about counterclockwise rotations. When you get into pre-calculus, you'll do some things called vectors, and you'll talk about being able to rotate at different degrees than what we're going to do in here. In geometry, we're going to talk about certain angles of rotation. When you get into the vector stuff in pre-calculus, you'll get into how to move an object different degrees. Like if you want to move it 37 degrees around a different point, there are ways to do that. The geometry concept that we just need to be able to rotate it certain degrees and around the center is what we're going to do. So it's kind of going to be like the translation. You're going to get a rule for a 90-degree rotation counterclockwise. Remember, counterclockwise is going to be to the left. So wherever it's sitting, counterclockwise goes this direction, 90 degrees. So 90 degrees, whatever the original ordered pairs are, a counterclockwise rotation by 90 degrees, it's going to swap X and Y and change the sign of Y. It's kind of a memorized thing here that you need to kind of commit to memory. 90 degrees counterclockwise, swaps X and Y, changes the sign of that Y value. So, and then 180 degrees takes X and Y. The original vertices or corners of your whatever object are you have that you're rotating, and it negates X and Y. That's all it does. Just changes their sign. Opposite of X and Y is 180-degree rotation. And then the last one is 270 degrees. You take your original ordered pairs of the vertices, and you're going to swap X and Y. Swap X and Y and change the sign of that X. Those are going to be how we do these rotations out of that. So 90 degree, swap X and Y, change the sign of the Y. 180 degrees, just change both signs. 270, change X and Y, change, and then, or swap X and Y, change the sign to X. That'll be a 270-degree counterclockwise rotation. All right, so let's look at a couple examples, or about 3 examples I think will get us everything we need here. So again, we're going to have the pre-image and then the image. So triangle ABC has vertices 2, 7, 6, 5, and 4, 1. So I'm going to graph that. Triangle ABC at 2, 7, 6, 5, and C is at 4, 1. Draw that, the pre-image. And a 90-degree counterclockwise rotation takes those vertices, and for the image, A prime is going to swap X and Y from A and change the sign of the Y. So that'd be at -7, 2. And then B prime would be at -5, 6. And C prime would be at -1, 4. Plot those points. And then C prime is at -1 and 4. And there you draw your image. So rotating that image 90 degrees counterclockwise. It's like picking it up and just rotating it that way is what they've done there. Not quite as easy to visualize as the reflection was.
Mr. Isbell?
Yes, ma'am.
Haley Combs checking out.
All right.
Thank you.
Thank you. All right. Number 2 is a 180 degree rotation. Technically, it doesn't matter what direction you do 180 degrees, because if you rotate 180 degrees counterclockwise, it's the exact same if you rotate it clockwise, because it's 180. It rotates it the same way. So, square.
Thank you.
Yep. PQRS vertices are 2, 6, 6, 5, and 5, 1, and 1, 2. So we're going to plot those points. 2, 6, 6. Q is at 6, 5. And R is at 5, 1. And S is at 1, 2. Not 2, 2, 1, 2. There we have our square. And we're rotating that with a 180 degree rotation. What happens to the ordered pairs for P prime? Sign changes is all it does. So -2, -6. -6, -5. -5, -1. -1, -2. Doesn't change the order of them at all, just changes their signs. And then we're going to plot that. So -2, -6. There's P prime. Q prime would be at -6, -5. And S prime is at -5, -1. I mean, that's R prime, excuse me. And S prime is at -1, -2. And there we've rotated that 180 degrees out of that. All right. Questions about those two? It really is just that easy. Just memorize those rules about the ordered pairs. That's all we've got to do. Let's look at number 3 and get a 270 rotation, and then we'll just move on to symmetry after that, because it doesn't change anything after this. Okay, so we've got trapezoid JKLM with excuse me, vertices at 3, 4. So I'm going to plot that. Six, 4. Eight, 1. And 1, 1. I can get by without using a straight edge, but I can't. It's not quite steady enough today. So we have a trapezoid there. And then the rule is that it swaps x and y and then changes the sign of x. So that's going to be 4, -3, 4, -6, excuse me, 1, -8, and then 1, -1.
I thought it was swap X and Y.
Did I not do that?
Okay. No, never mind. We did. I just looked at it. I'm sorry.
It's okay. Because it's very possible. Y'all know I make mistakes. Ask Rylan. I make mistakes. This time I didn't know. So you can ask my wife if I make mistakes. She's for sure. She knows. So let's plot those points. So 4, -3, J prime, 4, -6, K prime, 1, -8, L prime, and then 1, -1, M prime. And we see that same shape, exactly the same size, just rotated 270 degrees this way. Now, a little bit more advanced idea here would, if you wanted to extend this a little bit, would be what clockwise rotation, which would be this direction, would be the same as a counterclockwise of 270. You got to think a little bit about a circle and degrees and all that stuff. This kind of relates to what comes back to teaching in pre-calc. Yeah. 270 degrees counterclockwise. So we think about a circle, and I draw the cross in there because this is 90 degrees. Here's 180. Here's 270. And then 360, 0 and 360 are at the same place, right? All right, so 270 degrees counterclockwise would be like starting here at 0 and going around here. How many degrees is that clockwise? 90 degrees clockwise is the same thing as a counterclockwise move to 70. 90 degrees counterclockwise would be how many clockwise? 7. Same idea there. So that's maybe an extension of that. No, we don't get anything that really too much more difficult than what we just did on those 3 examples. The rest of those examples, you're welcome to do those for practice if you want to, just to make sure you've got the shapes and plotting points down. But I think you guys got that. That's not something I think you need to spend a ton of time doing. So let's skip over to the symmetry lesson. I think this is number 10 in our pursuit here. So 3 different types of symmetry that we're going to talk about today. Line symmetry. That's where you have a mirror image. So you could draw a line down through that picture, and it would fold perfectly and match up. So for this triangle that's over on the right, where would that line symmetry be? Right down the middle through that vertex up there at the top, right? So we put that line right there. That's the line of symmetry for that particular shape. Okay, so I'm going to draw that line of symmetry in there. That's the idea. A line symmetry is there's a place that you can draw a line. Doesn't necessarily have to be perfectly vertical. That line can be vertical or it can be at any angle. It doesn't have to be perfectly vertical or horizontal to be a line symmetry. The line can be drawn kind of in any direction there, and it's a linear symmetry out of that. All right. The second type is what's called point symmetry, and it's a rotation of the figure 180 degrees about a center point. Nice little block N letter there. In the parentheses underneath that, it means it looks the same upside down. So if you take your picture, I can't really do this with my TV, but if you take your paper and turn it upside down, does the N look exactly the same? Yes. So that is a point symmetry. The point is right in the center of that N, and that's pretty close to that maybe. So a point symmetry is you take the picture and turn it upside down, it looks exactly the same. If you turn it upside down. So point symmetry happens when you can flip it over upside down and it looks the same. And then the last one is a rotational symmetry of some rotation less than 360. And what you want to think about is a pinwheel. That if I rotate this picture of the sun, just think about these as points. If I just click it one point this way, does it look exactly the same? Yeah, if I click it 2 points that way, does it look exactly the same? Yeah, it does. So you could rotate that picture and it ends up being the same. That's a rotational symmetry. And we're going to look at several examples of this just to get the idea. So again, rotation, and we're rotating, and I'm just drawing that arrow up there to say rotate for rotational symmetry. So think of things that look similar to a pinwheel, or in this case, a sun or something. Yeah, it can be more than though. Yeah, that would definitely be more than that. A lot of the time, if it's rotationally symmetric, then it's going to be one of the others as well. Okay, so yes, it definitely can be more than one, and we're going to see that as we do the examples here. There's going to be more than one out of that. So let's look at those examples there. Number one. It would be all three because I could draw a line. Technically, I could draw a line straight down the middle there, and that would be line symmetry. I could also draw a line, horizontal straight through there. That's line symmetry. So I can do several different directions. If I drew a line that way, that's line symmetry. So it has line symmetry. And if I have a point, it looks the same upside down too. If I pick my, flip my paper over, it's exactly the same. So it's point symmetry. And then if I rotate it, it does the same thing. So this one is all three. So, and that happens, I won't say all the time, but it's quite common for it to have more than one. The next one, all three?
No, it's not.
I know it's line symmetry because it's just like my example we had earlier, right? And then, why is it rotational? Why not point?
Because if you turn it upside down, it's gonna be, it's not.
If you turn it upside down, it's that triangle, not the same. It doesn't look the same. It's got to match the original picture. So line and rotational there. It's rotational because that triangle is meant to be all the sides equal, and you'd have to measure it to know that, but that's what's meant to be happening there. Number three.
That is point. If you turn it upside down, it's the same.
All right, so if I flip that upside down, it is the same, and it is. And then, is that the only thing?
But lines aren't gonna equal.
Line won't work here because if I draw a line diagonally, it doesn't match up. If I draw it vertically, it doesn't match up. There's really no way to draw it.
And if you turn it one time, that's always gonna be.
So if I turn it once, that it doesn't look the same, right? Or 90 degrees, it doesn't look the same. What if I turn it twice, or 180 degrees? It look exactly the same as it is now at 180 degrees, which is less than 360. So the whole idea of rotational symmetry is that it's a rotation of less than 360. 180 is that. So it is rotational and point.
If anything is point, does that mean it can also be rotational?
Good question. What do you think?
Yes.
Okay. Let's see if we discover that here. Number four.
I don't think that's none.
You don't think it's none?
I think it is none.
Oh, okay,
Sorry.
okay. Double negative there, English language. It is none. That one doesn't fit any of those. What kind of right triangle would be line symmetric? What has to be the same on the right triangle for it to be symmetric? Yeah, those legs, have to be equal. The sides of the right triangle have to be equal, for it to be symmetric there. All right, number 5.
It's long.
Okay, we could draw a line. I could see, one, I could see one right here, right down the middle would work. If I turn it upside down, is it the same? No, so it's not point symmetric,
But it is rotational.
but it's rotational. So, Logan, let's go back to what you said earlier. If it's point rotational, is it automatically, or point symmetric, is it automatically rotational symmetric?
No.
I don't know. Does this one prove that or disprove that?
It's good.
Does it? It's rotational, but it's not point. So if it's point first, does it make it rotational? Let's look at number 6. Point rotational or point symmetric, is it rotational?
Yeah.
Because if I rotate that 180, I think it's going to be the same. So yeah, there's one that maybe supports that idea. What about number 7?
It's just long.
All right, line definitely couldn't flip it upside down. And if I rotate the letter A, it doesn't look the same at any angle. Lightning bolt for the flash.
None.
None. Definitely doesn't match up. Now that.
These are not my questions.
Are they? Yeah, this stuff's pretty easy stuff. What does number 9 look like?
Did you draw a line through it?
Could I draw a line through it?
No.
Never mind. No.
I could draw a line through it, but does it make it
No.
symmetric? I definitely can draw lines through it. It'd be point and rotational because it looks like a pinwheel. I don't know what a pinwheel is.
Yeah, that my grandma used to.
A pinwheel? What you use a pinwheel for? You mean a spinning wheel?
There you go.
There you go, a different thing. Pinwheel's that little thing that wind blows through it and it spins. That's a
Isn't there
pinwheel.
something about a Disney princess who touches a pinwheel?
I don't know. I don't, dude.
That's it.
Is that what it is? All right, number 10. That hourglass kind of looking shape there is what they're trying to shoot for there.
Rotational.
Line.
No, it's all there because you put a point in the middle.
Okay, if you put a point in the middle and flip it upside down, it does match up. So it looks
No,
like
it's not rotational because if you turn it one, it's on the other side.
if I turn it 180,
Yeah, it does.
it does work. Well, again, there's another one that maybe supports Logan's idea about point symmetric and rotational going together. 11, letter R.
None.
It is none of them.
Line for 12.
Could be for Reese too. Her name starts with. Alright.
Line.
Number 12 is line. Anything else?
And probably rotational.
Is it?
No.
Definitely not rotational.
What?
It's a different size on the top and the bottom. If it were, the same size diamond or rhombus, this is not rhombus. That's a kite shape. So definitely not.
This is line.
And rotation.
Line and rotation. Not point.
Could it not be point?
No, because if you flip it over,
Flip it upside down.
Yeah.
It's kind of like a triangle. It's upside down, kind of shape there. It doesn't work. 14.
Point and rotation.
Point. You flip it upside down, Z looks the same, and rotational. 15.
All three.
All 3. Yeah, good job. Queen of Hearts. Is it?
Point.
How's that line? Show me the line.
It's not horizontal.
If I do it horizontal, the Q's coming down here, not there.
It's point.
Rotational and point. It is not line symmetric. 17 is none. I agree.
18 is not. 18 is line.
18 is line.
Sideways.
Yeah, your horizontal line.
Yeah, that's hard.
All right. 19. Cycle symbol. Rotation.
And
Could it not be point? No, because you can flip it upside down. Never mind.
Yeah, it's triangular kind of in shape, so it is.
20 is
Snowflake.
point and rotation.
Line, point, and rotational. Boom, that's easy stuff, right? All